over to you. You can start the session.
Hello.
Yes, sir. Your voice is coming, but it's slightly low.
Okay.
Now it's fine. Now it's fine. Now it's fine.
Okay. Is it voice like high or low? Little bit low.
And now it's okay.
Now it's okay. Means it's appropriate for the talk.
About now, sir?
Yes, sir. It's fine. It's fine. You can go ahead with this setup.
Okay. So there is audio settings. Is there anywhere I can increase volume?
Now it's perfect, sir.
Fine.
Okay. Great. Okay. So fine, sir. So let me start. Yeah. Yes. Thank you so much, Dr. Pillai and the hosts from MNIT, once again giving me the opportunity to participate in this FTP. So like Pillai sir was asked, so let me share my screen and start further. Okay. So I guess you can see my screen, right? Yeah.
Yes, sir. It's visible.
Yes. So right. So this is the manual foundation, like this AICTE minor manual. So as per this, we are covering QT-02 Foundations of Quantum Technology. Probably, it is highly likely that you might have covered from the very start. All right, let me increase this. Yeah. So some quantum mechanics might have been covered. Okay, and the postulates of quantum mechanics. Right. I hope this is the one. Right. Yeah. And when it comes to right, so some quantum computing is being taught for you people. Okay, so I was asked to cover from here actually. Okay, right, even this spin-off particle systems. Okay, so that also I would like to cover. Okay, I will not be covering spin and angular momentum. That is a bit lengthy. Okay, right. So I was asked to cover basically statistical physics, this much part, right? Okay. So let's do one thing. So very good morning to all the participants. I hope you people are having a fun time and learning, right? Okay. So let me see how many are there. 200 plus candidates are there. Okay. Right. So now, how we do is probably you might have had presentations throughout, continuous presentations. Okay. And with the presentations, you might be listening through everything. Okay. What we will do, as you can see, right, this is more of a basic fundamental physics, you see. All right. So having a presentation would be, I would feel it's not that much effective. So what I'll do, I'll show whatever possible with the presentation. When it comes to the understanding of the concepts, what I'll do, I'll try to use my hand notes. Okay, and I will explain the concepts neatly, point by point, very slowly. Okay, right. Having the concepts understood, you can go ahead and read through the lecture notes which I'm going to share later. Okay. After that, what you can do, you can go through and understand and have a better understanding of the concepts which I'm actually planning to do. Okay. Right. If you happen to have any doubt in between, please don't hesitate. You can stop me at any point and ask me, and I can go back if needed, or I can bring something new which is not said so far, and I can like recollect or borrow from some other concepts which need to be used for the understanding of the current concept. That I will do, and I'll ensure that we are actually on the same pace as we progress through. Okay, right? So yeah, I have opened the another tab, another system where I can see the chat message if any. Okay, so I'll keep a tab on that if there is any message. Okay, I hope the audio connection and all is fine by now. Okay, fine. Okay, so let me go to the actual business. Okay, right. So since we are on the right. Okay, I hope you can see my slides. Let me go to the slideshow. Wait a minute. Slide. Okay. Slideshow. Where do I find the slideshow? Just a minute. Somewhere.
The top right corner.
Yeah. Thank you so much. Yeah. Okay. Yeah. So the question I would like to ask first of all is, why do I need to study this statistical physics? As you can see, the quantum technology 02 course, if you see, some quantum physics or quantum mechanics is involved, which is followed by some quantum computing. Okay, right? So why this statistical physics is coming in between? It's a very tricky thing, right? So I am fine with the qubits and processing qubits and designing the circuits for processing qubits and then doing some calculations and so on. Why this is statistical physics? It's not an easy subject to understand when it comes to the branch of physics. Why to study this? Okay, right? So that's the first question I would like to ask myself, or you should ask yourself when you want to get into the in-depth quantum computing. Okay, right? So let's try to answer this question in next half an hour, and then go to the actual part of statistical physics. Okay, right? So let me go to the next slide. Okay, I will try to answer why to study statistical physics. Okay, from each slide. See, here is the slide says foundations of quantum statistical mechanics. Okay, it's here I have clubbed the quantum mechanics with statistical physics and said some foundations from that particular clubbed version I will take. Why do I take? Okay, the first question is, as we are seeing, quantum computing involves many quantum states. Okay, what I mean is, you start processing qubits or realizing a qubit first and then adding another qubit to it, and you realize higher dimensional quantum system. Okay, so if you want to process a data additional data, you need to add one more qubit. Okay, so basically you are talking about various qubits coming in the vicinity to each other, interacting, and they evolve in time together. So I would use that evaluation together as a means to do the calculations, to do the computing. Okay, so here if you see the catch there, the qubits are interacting with each other. Okay, so they are like entities which are interacting with each other. In fact, it is some combination of many systems. So it's a many particle system or a many body systems. So basically when they interact, they evolve in different way. Okay. Now the problem for me is if I don't know how they interact, I can't define my quantum circuits. Okay. I can't expect the result as per my requirement if I don't know how they interact and evolve. So to know that, we need to exactly study them. The way they interact, the way evolve is actually dictated by a part of quantum statistical mechanics. Basically, it's a huge branch of physics where when I go to tiny level like atomic, subatomic level, I would bring in the laws of quantum physics, that is quantum mechanics. If I talk in terms of, or if I just bring in the statistics there, the probabilities there, then it becomes a statistical view of quantum mechanical dynamics. There, I would, in a way, actually, I'm going zooming out. If I go to quantum level, I'm talking in terms of single atoms. When I just zoom out slightly so that I have many qubits together interacting, it is in a way becomes a macroscopic system. There, I would bring in the probabilistic natures, the statistics there. I would be need to study that. So the statistical part there would tell me how the system would interact and how the systems are interacting and evolving. So I need to do that. I need to study the statistical physics. Okay. Like I said in the second point here, the statistical physics helps me to understand or to handle the interaction and to handle the probabilistic outcomes altogether. Okay, right? And this statistical physics, how it does the job for us is it gives me something called a partition function, a concept, a variable, or a term, which is a function named after named as a partition function. You, as of now, if you don't know what is a partition function, let's take this is something similar to density matrix what you have come across so far. Okay, you might be seen the density matrix formalism in your the recent lectures. So it is something close to that. So what I'll do, I'll use, or anybody can do, is use both of them, the density matrices and partition functions, to have a better understanding of how quantum systems or the quantum many body systems interact and evolve in time. Okay, right? So let me go further. Okay, so one more problem for me when I am talking about quantum systems, as you guys know already, they are very, very fragile, highly sensitive. That is where we need to cool the quantum systems to undertake the computing to millikelvin. That is how you see, like IBM have huge this cryogenic cylinders. Inside that there is electronic chips. It's called the transmons. So where the transmon chip is being cooled to millikelvin so that it is alienated or separated from the external noisy environment. Okay, so why the noisy environment I'm calling? Even a slight improve, like a high in the temperature around, would disturb its quantum mechanical nature. Okay, so because of that, one has to study how these quantum systems are so sensitive to these thermal fluctuations around. Okay, so there I would be using statistical physics. That is a very handy tool. Okay, and you probably have seen already there is a decoherence. The coherence in the system is very much required to undertake the computations with a steady manner. Okay, the qubits are supposed to exist steadily and their stability should be there. But if they don't, they, like say I'll take certain number of qubits, I assume that they will be in coherence, but it is not. because of the thermal noise, some of them at the boundary probably may get interact with the surroundings, and they may go out of the control, out of the picture of coherence, and they behave as if they are not in the group. They become outliers. So in that case, I would presume that I would taking all of them into the picture and doing the calculations, but some of them are going out and they are actually bringing in the noise. So that would lead me to the wrong conclusions. Okay. So there, which of them are prone to such kind of a behavior? If I want to know, the statistical physics would help me to do that. Okay. Right. So let me go to the, okay, let me change my screen. Yeah, just a minute, guys. Yeah, fine. So, yeah. Do I need to do the screen sharing again? Yes, I have to do. Oh, it is already sharing, yes. Okay. So the statistical physics allows me to study the thermal noise and the induced decoherence. Okay. Right. So, and it also allows me to understand, means indirectly it allows me to also come up with a model, some technique or something where I can mitigate those noise. Okay, basically that is what required. Okay, so right. Yeah, fine. So let me go to the next part. Okay, and what is so statistical physics or thermal physics about it? It is the statistical physics. If I say it is about studying the thermal fluctuation, studying about the temperature of the system. Okay, so if I try to do it at a very quantum level, so probably I may need to bring the quantum mechanics plus thermodynamics there, the idea of two concepts merging, so which I call quantum thermodynamics. Okay, so quantum thermodynamics is actually a part of statistical physics. Okay, so which allows me to explore the system, if there is any disorderness in the system, or what is the efficiency of the system to behave as per my wish. For example, if I try to take a qubit and embed information into it, means feed the information into it, I feed the information and I take the information out, that is decoding the information. So here I am putting the information and retrieving the information. So this process of putting and retrieving is actually depends on how effectively I do, the fidelity of it. Okay, so the fidelity would dictate the entire quantum protocol. If I take any protocol, let's say anything if you have studied so far, teleportation or dense super dense coding or anything, it all depends on many quantum systems inside, many qubits inside. So I have to, at every stage I should have a perfect fidelity. Okay, so the entire thing of protocol efficiency is actually dictated by the disorderedness in the system, how much work is done in the system. All those things are there. If I want to study them, I would be needing this quantum thermodynamics, so which comes along with statistical physics. Okay, right? For example, there is these days. Okay, so people are trying to study the quantum computers, even possibility of quantum computers at room temperatures. Okay, so if you can get the room temperature to be superconductors, then that is straightforward. Fine. So there the thermal systems are involved, the temperature is so much involved. So let's call them quantum heat engines. Okay, so there I would be needing to study them using quantum statistical physics. So the moment I study, it becomes easy for me to go ahead and develop a good understanding and do the required quantum computing. Okay, right. Okay, so like there is something entropy exists in. Entropy means the orderness or the disorderness in existing in the system. Okay, for example, if I just take a beaker of water and just drop a ink drop, it just goes system slowly and drops in and it starts spreading. Okay, initially it is nicely placed in one place, it spreads around. Okay, right, that is one way of seeing the things. Another way of saying is, let's say I have a same beaker, water is there and water is at the room temperature, I don't see any movement here and there. If I try to increase the temperature of the water by boiling the beaker, I see because of the increase in temperature, particles goes in here and there. I would see a haphazardous motion of the particles. So there I'm increasing the temperature, I'm increasing the disorderness there, thermodynamically. Okay, so when it comes to quantum computing case, I have quantum information fed to the quantum systems, which need to be used for computing. Okay, there whether there is information is have some disorderness. Okay, so is there an entropy, and that disorderness could also be used to get some useful results. For example, the entanglement, the correlation between quantum systems. The moment you have entanglement, you can do the teleportation. Okay, so and the moment you have all these things, you can create a quantum channel which can do quantum qubits can be sent through, and using the qubits you can realize the bits out of it. That is actually super dense coding. Okay, so all these things would involve the study of the entropy existing in the quantum systems. So this is the entropy in the quantum systems, the computing context is analogous to the disorderness existing in the thermodynamical system. The beaker, water beaker, like water in a beaker example, which I gave earlier. Okay, another simple example, if I had to give, if the students are sitting in a classroom, if I close the entire windows and the entire door, if I raise the temperature, what happens? The students goes haphazardly here and there. It's like a Brownian motion, like a random motion. People are going here and there. So that is what the disorderness in the system is being increased there because of the external intervention and increase in the temperature. Earlier, students were sitting nicely along the rows and columns of the tables in the classroom, but with the once I create a situation where I want to increase the disorderness, I can do that. So there I will study the disorderness in the thermal system. But when it comes to quantum computing, I need to study the disorderness, the entropy in the information connected to the entanglement that is actually borrowed in like concepts, the way dealing in statistical physics, this disorderness could also be dealt same way here, and then we can use that same von Neumann entropy, the formulae and the concept here, and carry further the quantum computing. That's why you need to study statistical physics. Okay, fine. So the moment, let's say you are equipped with a good quantum like quantum computing protocols. Okay, so you want to do some machine learning tasks using the quantum hardware. So there you bring quantum algorithms. Okay, right. So the quantum algorithms would simulate statistical ensembles. Okay, for example, if I just take a photosynthesis in the plants, okay, so the photosynthesis would occur with the utmost accuracy, very high accuracy compared to our solar cells, what they're doing right now. Okay, why we are not able to do perfectly, why these plants are doing perfectly is they're actually following quantum principles, quantum physics based principles. Probably they know how to deal the statistics. There are so many paths to reach the highest accuracy, and some of them are lower accuracy. So plants would take the exact path to reach the high accuracy, and they know it. They know the statistics there. So if you are trying, like if you are able to equip ourselves with this statistical physics, which deals with the ensemble of scenarios, means a combination of many scenarios. If I am equipped with study of those things, I'm fine. I can do the computing, quantum computing, much more effectively. Okay, right? So the same thing is used in quantum Boltzmann machines. We'll see what is Boltzmann statistics and all as a part of this lecture series. Okay, and this is also supports the generative models and the Monte Carlo methods. Okay, right? So it's all about the machine learning algorithms. Okay, for example, I want to simulate many body systems. Okay, quantum computer simulates complex quantum systems. For example, one of the main applications of the quantum computing or the quantum machine learning as of these days is studying the biological tissue. Okay, the moment you know how, for example, protein in a tissue behaves, how it folds. Every protein, when it folds in a particular form, it has got its own functionality. If I have a protein of certain folding, it does some task. If I know the folding of a given protein, I know what is it is doing, and I can also create a drug, a medicine, which needs to be treated, which needs to be used to treat, for example, a tissue having some issues with it. Okay, so the applications of quantum computing there, quantum machine learning there is the drug design, the medical applications. So there, I would be studying interactions of many particles, for example, electrons in a molecule. If I just take a molecule like a caffeine, many people will always quote or give an example just to study how caffeine actually interacts with our body once you take a coffee, and how it gives some kind of a energetic state, high state, how we should understand how it get dissolved, how it interacts, right? So if I want to study, I want to see what are the particles or the many bodies existing in a single caffeine molecule. There are more than 100 number of individual particle entities there. Because of one presence, the other will behavior will change. So altogether, they're actually interacting with each other. Okay, so to study that entire caffeine molecule, I need to treat that entire many body system effectively. I can't study in a laboratory. So best way to do is doing a simulations. Okay, to do a simulation, to come up with a model itself, I need to know how they behave statistically or thermodynamically, and then I can come up with my model which exactly depicts them. So that is very much required, and statistical physics helps you to do that. Okay, all right. When it comes to applications in material science and quantum chemistry, there it go. Right. So for the drug design, right, to study the quantum chemistry, how different chemicals interact, you would be needing the statistical physics, and I would be using quantum computer to study them. Before studying them, before creating a model, what model captures the exact essence of that particular system, right, is done with the help of statistical physics. Okay, right? So one more application I would give, a hardware itself. If you want to design a quantum computer, okay, as of now there are so many different kind of quantum computers have been defined or designed so far. One is transmons, electronic circuit based quantum computer. Qubits are realized with those transmons. Okay, and another one is neutral atom based quantum computers and ion based quantum computer, and another one is within a diamond you can embed or you can dope nitrogens, and you create something called a nitrogen vacancy. From there also you can realize qubits within a diamond crystal. From there also you can realize qubit and memory. Probably you might do computing also, you may realize quantum computer there. Okay, so then And even with using photons also, you can define a quantum computer, photonic chip based quantum computer. That is also being explored. In all the cases, if you see, one or the other way, hardware is involved, different kind of a hardware is involved. Different hardware, in the hardware, different entities are interacting. To know how they're interacting, how they evolve with an interaction, I would be using statistical physics there. Okay. And moreover, if you just see the trend of all the existing quantum computer except one or two, like the NV center based hardware, everything more or less requires cooling to millikelvin or less than that. This is because you want to remove the external environmental noise. So the temperature is involved there, the factor of temperature. So I need to study that and I need to understand and go ahead about it. Okay. Right. So the superconducting qubit behavior, the currently the transmons. Okay. So those are actually the behavior of them actually understood from the statistical physics. Okay, fine. So this is, if you just go through all of the slide by slide here, the statistical physics there all the way from simulating a many body system which allows me to do the hard computation, and actual quantum computer realization. Up to that point, I have to go through all the statistical physics based understanding and then do the quantum computing. So that is the main essence why I need to study the quantum computing, or statistical physics. Okay, right? So if somebody has anything, please chat type. I will just uh, discuss that. Okay, right. So this is the, okay, let me go out of this. Now we know why to study statistical physics. Okay, let me use my hand note from here onwards. So I would be really needing my hand note to explain. Okay, fine. Okay, so let's try to start with the statistical physics. Okay, fine. Okay, you can see my screen now. Yeah, right. Okay, let me just say I will be starting statistical physics. Okay, right. And first thing is I study something using statistical physics, right? Okay, so what is that thing is a system. Okay, a system could be composed of many things. Okay, so let me take a system. Okay, let me take a system. Okay, system means something which is composed of system. Okay, just a minute. One minute. Just got hanged. Yeah, a system. Okay, what has happened? Okay, just a minute. Yes. Okay. So a system consisting of particles. Okay, it consisting of many particles. Okay, so here the system can have interactions. Okay, what is happening? Just a minute. System can have interaction. The particles would interact. Okay, so the interaction could be strong and interaction could be weak. Okay, right? So for example, if I just take a gas, okay, the particles, if you just take around us, the gas around us, it has particles with weak interaction, weak interacting particles it has. Okay, and strong, probably liquids and solids where the particles are together, too much together, so that is where probably interaction may be more. Okay, so when it comes to gas, the interaction would be low because they are further apart. Okay, so that is what usually I would take when I want to study something consisting of particles. Okay, so here the weakly interacting case, let's take. Okay, so weakly interacting means let's take electrons. Okay, electrons are atoms. Okay, are molecules in a composite system. Okay, if you just take these examples, okay, I can study them by assuming there is a strong interaction or where there is a weak interaction. If I just take electron gas, they are further away from each other, so that means I am treating them as a system of weakly interacting particles creating a composite system. Okay, now so let's keep it aside. That is what is the system is. Okay, so what is a system? Definition is that. Okay, right? So now let's see from different prospect. If I just zoom out, come further away from the system, okay, probably I might have many systems together. Okay, what I'm doing, I'm trying to combine many things. I'm going to see things at macroscopic level. Macroscopic. Okay, so here I cannot say anymore atoms, electrons or molecules. I can't say. I have to talk in terms of group of systems or group of electrons or group of atoms. They're very huge in number. Okay, so that is where the macroscopicity would come very large, like a classical world. In a classical world, what we see is things are certain. If I just take my mobile, it is there. Okay, I can touch and feel. So this is, if I just take such thing, it's macroscopic in size. Right? So there, if I want to specify things at the macroscopic level, systems, if I want to specify them, what I would be needing? Definitely, I would be needing system location. Okay, system location I want to specify. And it's, if it is moving, let's say it's moving with some velocity, multiply it with mass, I would be finding its momentum. Okay, if I just take one system, macroscopic system, it is defined by its location, described by location and momentum. For example, if I just take a combination of many such systems, okay, many systems together, what I would be needing, I would be needing a position coordinates, I would be needing coordinates. Let's say call QIs, position coordinates. Okay, position coordinates in the sense where the system one is located. Okay, and I would also be noting momentum coordinates. Let me call momentas, pi. Okay, so this is a linear momentum, linear momentums. Okay, so where I, if you just take the index, would run from 1, 2, and so on, let's say n, where the n systems are there. Okay, for n systems, to describe the system, I would be needing qi, positions and momentums. I would be needing. Okay, so at a macroscopic level, I'm talking about. So one thing here I have is I'll see things from the very zoom out manner. Okay, so here the things are like, say, if I know the position momentum at, let's say, at a given time, if I know, let's say I know that, sorry. Okay, so I know momentum, position momentum at known, okay, at some, let's say, t0 time, I can predict or determine in later times. How? I can find at t final, sorry, pi at t final, I can find. How? Just there is a connection between them, something called, there is equations of motion. Equations of motion are there, they connect them. Let's say simple Newton's laws. Okay, Newton's laws could be used to connect them and find what is the final system coordinate values if I have known the initial values. Okay, so how it is done? Let's say there is a small change, in the given coordinate. By adding that small change, I'll get the later values. Okay, so infinitesimally very small. So the question here is, how do I get for very later times? Okay, very simple. What you can do, let's say I have a coordinate system q and p. For example, let's take a two-dimensional system. Okay, where given particle exists in coordinate q and p. Okay, the system is confined to q and p, means it can have position and some momentum. So I will represent a Cartesian coordinate system, like just like x and y. I'll have a Cartesian coordinate system where I have q and p. Okay, so for a given value, let's say system is existing at some point. Okay, let's say this is a qi pi. Okay, so what happens later times? Later times means qi is slightly changed, pi is also slightly changed. So what I'll get, I can just divide. Okay, so I can just divide the entire thing into small intervals along the q, along the p. Okay, so this is q, this is p. Okay, so let's say system is initially here. Okay, so it changed to this point. Let's say this is initial, this is later. Okay, so how the system is evolved, how to find is, I just do keep on adding or subtracting the small changes to the initial values, and I'll get that the final values, that is qi t final, pi t final, by just doing the same addition or subtraction. Okay, right now, how this, it's like, to have a better accuracy, you can go to a smaller and smaller. What is advised is qi's and delta pi's are very small. Okay, so that means what I'm doing, I'm just trying to create a small cells, each cell which is having a volume of delta qi, delta pi. Such volumes I am just creating so that the system could exist in that particular single volume for a given initial location of that particular system. Where it goes, I can simply find where is that volume, which volume would occupy. So remember, this is a volume I am saying, it is called an area in this particular two-dimensional coordinate system. If it is three-dimensional case, it is actual volume. Okay, right? So this is how we define in the case of the system being studied in terms of classical mechanics, means the basic Newtonian mechanics. Okay, now fine. Now let me go to another way of saying things. Okay, right? So I zoomed out. Let me go a little bit zoom in manner. So let's go to the very close, means let's talk at microscopic level. Okay, means at the atomic level. Fine. At the atomic level, what happens? The quantum mechanics, quantum principles comes into the picture. Okay, means quantum principle or quantum physics rules are going to be used to understand how this macroscopic, at macroscopic level, things are behaving. Okay, so why that is so? Because if I just take an electron, for example, let's take electron. Okay, if what is its mass of an electron, which would be something like 10 to the power of minus 34 kilograms roughly. Okay, and if I have an electron, if it is, let's say I put the electrons to move around, let's say electron gun I can have, so the velocity of that electron could be something around 10 to the power of 8 meter per second, very close to exactly equal to the velocity of the light. Okay, if I have this combination, the electron system, okay, which is microscopic by the way, right? If I take that system, this system is so tiny, it is no more behaves like a particle. Because of this, behaves like waves, means it becomes probabilistic. Because of that, wave nature would come. That is vice versa. Because of wave nature, probabilistic nature will come, or because of wave nature, probability come. Probability leads to wave nature. Okay, so here de Broglie gave a nice simple equation. What he called is, if the particles are so tiny, okay, and if they are moving very close to the velocity of the light, in that case they behave like a behaves like a wave. Electrons behave like a wave with wavelength, de Broglie wavelength is equal to Planck's constant divided by mass into velocity. Here in this case, MeVe, which is close to optical wavelengths or optical frequencies. Okay, few angstroms, which is measurable by the way. If I just go a little bit higher than that, macroscopic level, the previous situation where I am talking about combination of many systems, there the lambda is going to be very small, very tiny. For example, if I just take a bullet, a traveling bullet, lambda would be so small, not able to measure, so small, not measurable. Okay, measurable. So that is why I would say the quantum wave nature associated to the bullet is very negligible. But when it comes to electron, there is a quantum nature. Because of the quantum nature, the duality would come. Behaves like a wave due to duality. Duality in the sense, at a given point, particles behave like a matter as well as waves. Which one, when, we don't know. As if it has got its own cognizance. Like say electron is traveling, when I'm not looking at it, it just behaves like a wave. When I try to touch it, it behaves like a particle, right? Okay, that may be the understanding one can have. Okay, fine. Now the question here is, the quantum like particles at the microscopic level described by this duality nature. Okay, so earlier I was taking the small change in the coordinate delta q delta p. Okay, so here in this case, how small delta p I can, delta q I can take. Okay, right? How small I can take, it's not as small as possible. This earlier I said I can take as small as possible, but here it is not the case, because the things are so small, they move here and there hazardously. I can never measure the velocity and the position accurately, so there is always, I will make a mistake in its position measurement, in velocity measure, angular momentum measurement, and its position measurement, which is given by upper bound h cross, which is a Heisenberg uncertainty principle. Okay, okay. So probability duality induces that. Right. Okay. So that means I can always the delta p and delta q here in this case, delta p is very small, I can take, right? Let me call delta q delta p earlier, let me call it is some h naught, some volume element. Okay, aerial volume element. So here in this case, the h naught delta p delta into delta q cannot be much smaller than h. Okay, right? Sorry, cannot be more than h. So it has to be always more than h. Okay, so that is the problem with the macroscopic world, sorry, microscopic world. Always there is a problem in getting things certainly. So there the probabilistic nature would come. So the probabilistic nature is induced, so which could be studied using statistical physics. Okay, right? Okay, so let's understand a little bit more with simple examples. Okay, for example, let's take a nucleus surrounded by an electron. I'm talking about Bohr model of an atom. Okay, so electron is around, so it is going around the nucleus. We know that when it goes around the nucleus with particular orbits, like quantized orbit they called, in those orbits if they go around, they will not lose any energy. Okay, they remain intact. Okay, now the electron is moving around the nucleus, it can possess a linear angular momentum, so that which is r into mass into velocity. This is a linear momentum. R cross p would be angular momentum. Okay, angular momentum means the electron would have a magnetic field due to rotational dynamics. Because of rotation, it can possess a magnetic moment. Okay, you just take the rotation curling of your fingers just opposite to the direction of the electron, the thumb would show the magnetic moment, which is the rotational magnetic moment. Okay, right? So one more thing is, if you just take the same electron, if you just take, to try to observe it carefully, the electron just like Earth moving on its own axis, it just rotates about its own axis. The same way, electron also rotates about its own axis. Okay, so the electron rotating about the nucleus would constitute a magnetic moment, right? Angular momentum, a spin angular, rotational angular momentum. Because of the electron rotating about, also gives spin angular momentum. Okay, so very simple. So why a spin rotational angular momentum? Angular momentum comes because of rotation about the nucleus, and rotating about itself gives spin angular momentum. Okay, so now it's the angular momentum can only have certain direction. a rotation about up, rotation with this, and angular momentum would be up. Rotation in the opposite way, clockwise or anti-clockwise, the spin would be pointing down. So if I just take an electron, it can have up spin or a down spin. So I can associate the up spin and down spin with some quantum number, some number, something probably you might have studied during your 7th or 8th and 9th standard. Let's recollect. It's called quantum number. Okay, so we'll come to that. What is a quantum number? Let me call it as spin quantum number. So spin quantum number would be spin quantum number will be equal to plus half when the spin is up, minus half down spin. Okay, for an electron I'm talking about. Okay, just like a rotational magnetic moment, even spin also would constitute a magnetic moment. Okay, so those magnetic moment is actually represented by the corresponding magnetic momentum would be my just a minute. Okay, so mu, and this would be minus mu. Okay, now the magnetic moment for an electron. Okay, now let's say if I expose that electron to the magnetic north and south pole, if the electron is there, by the way, it is rotating about its own axis. If I expose that, let's say there is a magnetic field lines, okay, north to south, right? So there is a H field, magnetic field is there, okay, H field is applied. In that case, there would be energy associated with this magnetic dipole moment. The electron would gain some energy by aligning towards along the applied field or away from the applied field. Okay, let's say it aligns along the applied field. So magnetic moment would be minus mu into H, where H is the applied magnetic field. Okay, if it aligns opposite to the applied magnetic field, then the energy would be plus mu into H. The formula is mu into minus of H. Okay, so because of that, I have minus comes in the align in the positive case, no minus in the opposite case alignment. Okay, so this is the scenario when an electron, if it is exposed to external magnetic field, if I don't, it will have a positive spin quantum number or a negative spin quantum number. So now the case, let's say if I want to specify combination of many electrons, such things, what I would be needing, I would be, let's say, combination of many such electrons. If I just take, so if I want to represent them, what I would be needing is, I would be representing using a wave function, which is a function of the coordinates of all the electrons. Let's say there is a n electrons, okay, and momentums, and also their spins. Okay, so let me call ms1, ms2, and so on, msn. Okay, so that many number of coordinates I would be needing to represent all those n electrons, n number of combination of many such electrons. Okay, now the question here is, the each ms would go plus or minus 2, plus or minus 2. Position momentum can take any value. Okay, right? So this is how I am going to define the system defined. Okay, system is defined using that. But in the case of classical system, I would be just needing position and momentum, probably energy of the system, probably volume of the system, probably temperature of the system, and so many things are there. But here, the wave function would help me to do that in the quantum physics case or the quantum mechanical or a quantum levels case. Okay, so right. So now let me take another simple example. Let's say again get back to electron within an atom. Okay, so these are electrons, few combination of electrons I have taken. Let's take electron within an atom. Okay, let me take in that case. If I just take an electron within the atom, so there is a nucleus, there is a ground state, there is an excited state, there is a further excited state. Let me call n equal to 0 is a ground, n equal to 1 is excited, n equal to 2 is the second excited, and so on. Okay, so here the each, like if I say electron confined to an orbit would be electron confined into an orbit, single orbit, could be treated using simple harmonic oscillator. Simple harmonic oscillator means if you just take a simple pendulum, okay, if you just take, okay, what did I do? I'm sorry, just a minute. Yeah. If I just take a simple pendulum, okay, it rotates, oscillates, right? The same way the electron about the nucleus rotates, it oscillates, right? So simple pendulum is actually simple harmonic oscillator. If I am studying that at quantum level, I am going to say it's a quantum harmonic oscillator or quantum simple harmonic oscillator. So if I study the quantum harmonic oscillator, I can get the energies of a particular orbit is actually represented in terms of the orbit number, which is simply this. Okay, energy of an electron in an orbit. Very simple. From quantum harmonic oscillator you can derive that. Okay, so if time there, I would show that how it is being done. Okay, now here n is actually principal, called principal quantum number. What it tells me, n equal to 0 is ground state. Okay, n equal to 0 is ground state, n equal to 1 is excited state, and so on, right? So here in this case, you see, using pure quantum physics, things are studied, and from there we study what is the energy of the system. Okay, right? Now, if I have to represent here in this case, there are so many atoms. Let's take a caffeine molecule, okay, or let's take a helium molecule, or let's say go from hydrogen and so on, higher and higher in the periodic table, the number of electrons would increase. So according number of electrons would be started piling up from each orbit, so on, later orbits. Okay, right? So the way piled up, let's say in particular orbit, certain number of electrons are there. In this case, the quantum state or a wave function representation would be having, let's say, the same set of coordinates, same set of momentas, and then I would have some, let's say, n1 to nn. Okay, so let me call a capital N just to avoid the confusion here. Okay, right? Fine. Oh, there is a problem with capital N also. Capital N is reserved for something else. Okay, so let me use small n only. Yeah, fine. So, right, this is how we will represent, okay, a quantum system or the many particles within an atom. Okay, so let's take out an electron out of the atom. Let's say take out the electron in an atom, put it in a box. Let's say there is a box, three-dimensional box is there, and electron is inside the box. Okay, so what I mean is, let's say the box is confined between, let's say, length x is confined within a length 0 to x, y is confined to 0 to ly, z is confined within 0 to lz. Let's say the box dimensions are that. Okay, and if the electron is confined within, in that case, if I want to know how this electron would behave, okay, so in that case I would be needing electron in a box or 3D box. Okay, so in that case I would be needing some dynamical equation which tells me how things behave. For example, in a classical Newtonian mechanics means classical physics, if there is a force acted on an object, generates an acceleration. Okay, so acceleration is what? Acceleration is mass into second order derivative of position is force. Okay, so if you just see this is a second order differential equation. Okay, you solve that and get what is the position in time for a given force. You would find for given F. Okay, this is a Newtonian mechanics for you. Here in this case, I have taken an electron and confined within a box. Let's say the box has zero potential. Okay, means no energy is there inside. In that case, how the system would behave is actually described by a Schrodinger equation. Schrodinger equation, probably you have come across this already. Okay, the Schrodinger equation is there. If I had to write the Schrodinger equation for current scenario, the electron particle in a box, okay, so I would be writing three-dimensional Schrodinger equation, Planck's constant, okay, 2m dou square dou x square plus dou square by dou y square plus dou square by dou z square acting on given quantum state. Let's say system is able to move in 3 dimension is equal to system can exist in various energies multiplied by x comma y comma z. Target is to find what is this. What is this? Okay, target is to do that. And what are these? Okay, so that is what I want to find. So it is analogous to finding x of t in a Newtonian mechanics. Okay, if you carefully see this equation, Schrodinger equation, if you carefully see, right, which is in fact second order linear differential equation. Okay, the second order differential equation. So the second order differential equation would bound to have sinusoidal solutions. Okay, so this sinusoidal solution bound to have sinusoidal or cos and sines. What I mean is, what is this? Prevent the space creating additional dialogues. Cancel. Okay. Okay, just a minute, guys. I'm sorry. Yeah. Sinusoidal solutions, which are simply, like say, some amplitude multiplied by some cos kx, sine ky, sine kz, where k is x, y, z, propagation constant along the particular direction. Simply that. This is the solutions. The solutions would be like this. Simple. So now the question is, if I just take the box at the boundaries, let's say at x equal to 0 or x equal to L or y equal to 0, y equal to L, z equal to 0 or z equal to L. Okay. In the boundaries at these locations, the psi must vanish. Okay. Must vanish. This is because there is no possibility to find the electron at the boundaries. So this used as a boundary conditions. I can use them as a boundary conditions and then find A and what is Kx. I can find them. Okay, if I try to do that using the boundary conditions, Kx is simply, what is this? Kx is simply is equal to, okay, you can easily find, right? So there is, okay, so Kx means just take this. When this is 0, when x is equal to 0, straightforward, implies sine Kx, x is 0, no issues. When x is equal to L, okay, sine Kxl must be 0, which means Kx implies Kx into L is equal to some integral number of some pi. Okay, right? Let me call n is nx. There are two more dimensions. So that means, which implies, okay, Kx is nx pi divided by Lx. Okay. Similarly, you can get ky. Similarly, you can get ky is equal to ny pi divided by ly. Kz is equal to nz pi lz. By using them, you can easily find what is the solution of the quantum system. Interestingly, the solution of the quantum system is very simple, is equal to sine nx pi x by lx. Okay, I'm sorry, this is x. Sine ny pi y divided by ly. Sine, okay, nz pi into nz pi z by lz. So this is a solution. Where is the A? You can ask me. Amplitude. Amplitude is actually becomes 1. You know why? The quantum states are always unit vectors, because the length of this norm is 1, so which implies amplitude is equal to 1. Okay, so now as you are trying to solve this equation, okay, so when you try to simplify that equation, when you convert that into a simple differential equation, non second order linear differential equation, so what it is actually is dou, for example, in one dimension, which would be plus k square psi equal to 0. This is the equation for one dimension case. The three dimension is reducing to one dimension if I do, where k is this. This is a vector, propagation vector k. For one dimension is a kx. So kx square is actually 2m e divided by h square. Okay, from you can see from here. From here, if you just rearrange, okay, from this is what you will get. So energy is equal to kx square h square divided by 2m. By the way, what is kx? Kx I just got earlier. Kx is nx pi divided by lx. So which implies energy is equal to, okay, nx square pi square lx square h square by 2m. Okay, so this is the energy in one dimension. If you want to find, this is, let's say, energy in x dimension. So energy in, let's say, all x comma y comma z in all the dimensions, if you want to find, you are actually summing them together. H square by 2m pi square nx square lx square plus ny square ly square plus nz square plus lz square. Okay, so the energy of the system is like this. The moment I know energy, I can study further. Okay, so here the quantum numbers are nx, ny, nz, which can start from 0, 1 and so on. These are the quantum numbers. Okay, So which would become a part of the quantum system apart from x comma y comma z. They also become nx, ny, and nz, and so on. Let's say px, py, pz are also there. Okay, so this is the state description. Okay, right? This is a let's slightly zoom out manner. Means I'm not talking very much at a microscopic level. I'm just trying to come up from the zoom out level and just trying to address it. Okay. Now, so we just saw so far classical as well as quantum level. Okay. The classical level, I will take a system as together. Quantum level is system where specifically I'll talk about a position, how much position I can accurately measure. Okay, so there is always a connection between quantum and classical. Okay, so in the classical case, if you just say to get the V final, if I know initial, I add some small quantity. Okay, right? So let me remove the subscript. Okay, let me call, right? Okay, so if I know p final, p initial, I can just add a small quantity and I'll get. Now I was talking earlier in terms of small cell dq into dp volume cell. Okay, so the accuracy of predicting accuracy of predicting accuracy of predicting new states is actually depends on how small the cell I am taking. Okay, okay. So predicting depends on h naught, which is dq into dp, to be very small, very small. Okay, but in the quantum case, okay, so delta q delta p delta p always has a upper bound, right? So here I can't have my h naught, okay, smaller than h cross. So h naught is always greater than h. Okay, right? So this is the quantum picture, right? Now we know how things are dealt at the classical level and the quantum level. Okay, so now try to connect them. Wherever we need a classical, we use classicalness. Wherever we need quantumness, we bring quantumness. Okay, so the difference, as you guys know, I just need coordinates for the classical, but I would be needing quantum state with the quantum. Now I'll put a hats on the on the variables, so which is just to refer they're the quantum operators. Okay, right? Fine. So let's say a system of electrons or system of atoms within a lattice. Okay, so if I just take a system of atoms within a lattice where they come together and contribute together and gives to some overall effect, that is a macroscopic effect. I'm sorry. Okay, so let's take a paramagnetic material, right? There each atom could align in the direction of external magnetic field or in the opposite direction of the external magnetic field. Okay, right? So because of that, what happens, the overall magnetic moment together would vary, but the number of particles would remain the same. Minded, the number of particle remains same. Okay, number of particles would remain same, but overall magnetic moment would change depending on the individual alignment of each atom. Okay, whether it is aligned towards or in the direction of applied field or opposite. Okay, now if I just take, let's say 10 atoms are there, if I just take 10, right? So if the external magnetic field is applied, let's say external magnetic field applied north and south for the 10 atoms, all the 10 can align in the direction of let's say external magnetic field. Let me call all the 10 plus 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 and so on, all 10. Okay, that is one of the possible state. Okay, out of 10, one of them is not aligned. Let's say the first one is not aligned, everything is aligned, another state. So let me call the state represented r equal to 1, state r equal to 2. Okay, so here the state r equal to 2, if you see one atom I said misaligned, which from the 10 anything can be misaligned. So there are so many possibilities here, so many possibilities. Okay, so likewise, if I just take this many electrons or this many atoms, the accessible state are possible, or it is also called accessible states, are many for the system to exist in. Okay, right? But overall energy can be varied. Okay, but the number of particles are same. Our total energy may vary. Volume can be same. Okay, so the information, some information is fixed. Okay, example, number of particles. One simple example. Okay, and some information, okay, would vary. Example, total magnetic energy. Okay, why? Because whether all of them are aligned and some of them are aligned, that would give us a different energy. Energy, if I just take, would vary between two values. Let me take energy vary between some E initial and some E initial plus some small change in E. So this is always exist in the statistical manner. If I'm just talking about a quantum systems or any system per se consisting of many things, so in that case I need to bring in the accessible states available to the system to existing in. Okay, now how many states are possible here in this case? 10, it's too many. For example, if you just take n equal to 3 atoms. Okay, so in the 3 atoms case, let me see, all the 3 can be aligned. Okay, and one of them is not aligned. Okay, so there itself I can have 3 more combinations. Okay, and let's say 2 of them are misaligned. Okay, and all of them are misaligned. How many I got? I got 8 combinations, 8 possible or accessible states. accessible states for the composite system. Okay. Composite. Okay. Now the question is, if the system is not interacting with external means, okay, let's say this is interacting system with the external magnetic field H. Okay, let's say it is not interacting, isolated. Okay, so in the isolated case, if you just say I may not get all the possibilities, okay, right? So only a few possibilities that only exist with the isolated system. But the thing you remember, okay, in the isolated case, if I happen to say, so three possibilities are there. Isolated case, let's say three possibilities. Only these possibilities in isolated case with only three possibilities. Let's say I said that. Okay, I can create a scenarios like that. Okay, so in the isolated case, what happens? Since there is no external intervention, right? Okay, so since there is no external intervention, what happens? All the accessible states are becomes equally probable, because so which, like say, all become this and this becomes equally probable, because to have unequal probability, let's say one of them is preferred over the other, means what? Somebody is telling that to go to that particular state. There is no one to do it, though no external intervention. As no external intervention, or intervention means external field is not there. So in that case, everything becomes equally probable. So that is the idea which actually I get from statistical mechanics. Okay, so the statistical mechanics actually says, or just gives a postulate. Okay, so from the whatever knowledge we derived, so we can come up with a postulate, or somebody else already came up with a postulate. So basic postulate they came up with, postulate. Okay, what is the first postulate? Is an isolated system, okay, let's say is in equilibrium. Means all the possible states are equal. Like say there are so many all the states are possible. Okay, right? So in equilibrium, in that case, all the accessible states would become equally probable. Okay, so it becomes equally probable, right? And this is only guaranteed when there is isolation. Okay, so when there is no isolation, I can't use this postulate, or I can't say this is exist in the system. Okay, right? Accessible would be equally probable, right? This is a postulate. Now I just gave you already an example. Okay, so the three systems together, right? Three let's say three spin systems which were exposed to external magnetic field. Let's say external magnetic field, let's say three systems are there. Okay, if one atom with a magnetic moment mu aligns in the direction of external magnetic field, so the total magnetic energy, it would be mu into h, sorry, minus mu into h, if it is aligns positively. If it is mu h, if it aligns negatively, alignment. Okay, right? Now I have three atoms which can align in any direction. Let's say the overall energy is just confined. Overall energy is confined to a value, okay, minus mu h. Okay, so overall energy is confined to mu h. In that case, what are the possibilities? So what are the possibilities in this case is just the same thing, plus plus minus, plus minus plus, minus plus plus. Okay, so these three are accessible states, right? So the external magnetic field is there. All the three may be equally probable. Okay, right? But thing is, if you go actual statistical physics analysis, if you do, you would see they are not equally probable. Okay, right? Why that is? Because why? Answer is there is interaction exist in between. That interaction, if I don't consider, I would lead into the wrong conclusion that they're not equally probable because of the interaction, right? Even one of them flips the other, it also gets flips. Okay, so there the balance would happen. In that way, the quantum states or the accessible states becomes equally probable. Equally probable. Okay, irrespective of even the external magnetic field here in this case. Okay, so now we have seen how quantum systems are the any systems at microscopic level and macroscopic level are dealt using statistical physics. Okay, now let's try to get a little bit more into the thermodynamics or the statistical part of the statistical part of the physics. Okay, so now there is a loss. There are thermodynamics laws. Okay, thermodynamics laws. Let's revise them. Probably everybody has gone through the thermodynamics laws, right? So there is a zeroth law. Okay, what it says is, let's say there is a system A, there is a system B, there is a system C. Okay, so system C is in connection with both A and B. I just drawn a diagram just like that. In equilibrium with A and B, then A and B are in equilibrium. Okay, that is straightforward convection. Okay, so another way of saying is if two systems are in thermal equilibrium with a third system, then they must be in thermal equilibrium with each other. Even then, let's say they don't interact with each other. Okay, they may through the third one they interact. So this is a very simple idea which could be used even when the qubits interact with each other. Okay, so analogy could be used for qubit interaction. Okay, done. Now there is a second law, sorry, first law of thermodynamics. First law. Okay, so we are talking about microsystem or a macro system. The statistical physics deals a macro system, like the combination of many microsystems together. Okay, so as per the thermodynamics, if I just take a macro system in the equilibrium, like earlier, characterized by some energy, E, internal energy, macro system macro system at a thermal equilibrium. I'll write the short form in my notes, everything is there. Okay, in equilibrium. Okay, described by, let's say, described by internal energy. Okay, let me call internal energy E, right? So let me call this E bar, internal energy. Okay, so if I just take a macro system, if it is isolated case, E would be always constant. We saw that example. Okay, means total energy would always remain the same because there is no external intervention to fiddle with the internal energy. Okay, let's say non-isolated case. If the system is allowed to interact with the reservoir, okay, interaction with the reservoir is there. In that case, what happens? In this case, definitely the internal energy would change. Okay, so internal energy is changing means internal energy is changing at the cost of some work is being done. Okay, somewhere the energy is being exited, right? Okay, so let's say to do that work, some external body has come in or external intervention has come. Okay, interaction with the reservoir. Okay, heat reservoir, it is there. So in that case, my god, this is, I have to start new. Just, I'm sorry with this, guys. Okay, external reservoir is there. So the internal energy would bound to change because there is a work done and some energy, some heat is being added from the external means. So this would be my macroscopic work done, and this is the heat added to the system. Okay, so because of that, this is always varies. Okay, right? So first law says, first law of thermodynamics, if the macro system at an equilibrium, let's say every accessible states are equally probable, if that's kind of a situation, if I consider, if system is bound to isolate, so total internal energy would remain same, otherwise it varies. Okay, right? So what is the connection of this to the quantum computing? If I had to answer is, let's say the qubits exposed to the environment. So basically not exact environment, so that is a temperature variation or issues with the cooling mechanism. Okay, if there is a issues with the cooling mechanism, qubits are exposed, their nature would change, their internal energy would change, their interactions would change. All those things need to be addressed, probably using this kind of a knowledge. Okay, so now the first law is done. Let's say come back to the third law of thermodynamics. Okay, so the third law of second law of thermodynamics is, we saw there is if I just take a glass of water, heat it, the disorderliness would increase, right? Even though system is in equilibrium earlier, temperature was room temperature. Okay, so same here. If I just take a macroscopic system at equilibrium, again macroscopic system at equilibrium. Okay, if I just take, okay, so there is a orderness in the system or there's disorderness in the system, right? Let's say described by entropy term. Okay, disorderness, entropy, let's say S. It is described by S. Okay, if it is thermally isolated, right? If it is isolated, and led to evolve. Thermally isolated, it's led to evolve. What we see is the change in the entropy would always greater than equal to 0, means disorderness is always increasing. Okay, that means the information disorderness in the case of quantum computing, information disorderness would always increase. That is what the delta S greater than equal to 0 say. Okay, but probably the overall energy may remain the same, right? Okay, so for example, non-isolated case, where what happens, change in ds would be actually due to amount of heat observed multiplied divided by some absolute T. Okay, so yes, definitely there is a change that is due to the dq being absorbed. Okay, so here system is actually undergoing undergoes a like a very infinitesimal change in the infinitesimal is undergoing very small changes. Okay, so each change would induce some ds change, which is actually dq by d. Okay, so this is what the second law of thermodynamics talks about disorders in the system. So in the case of quantum computing, we'll talk in terms of how information is being fed. Okay, so the entropy means disorderness, which could be used to study the entanglement. Okay, connected to entanglement. Okay, which is in fact connected to the purity of the system, purity or mixedness of the system. Okay, right? So through this we can study the entropy study. We can do the entropy study of the quantum systems. Okay, so there is a third law of thermodynamics. Let's connect the third law of thermodynamics to quantum computing. Okay, so here this the third law of thermodynamics says entropy S, if I just take for a system which would have a limit, it reaches to a constant, it can't change anymore when T tends to absolute 0 from the positive direction. Okay, so this is the here this is independent of any parameter of the system. Okay, so that constant reaching is actually due to temperature is going to very small values. Okay, so that is what people were trying to do in the case of transforms in the quantum computer. Okay, right? So having a lower and lower temperature to avoid the disorderness is very much important, independent of any parameter. Okay, fine. So by the way, if the system entropy is S, which is actually connected to the number of accessible states in terms of Boltzmann constant multiplied by natural log of omega, capital omega, where capital omega is actually the number of accessible states available for the system. Okay, right? So if the number is more, the ln is more, log of that number would give the appropriate number. So accordingly, we'll get the entropy values. Okay, so what you see here, how the thermodynamics is actually connected to the quantum computing terms or the quantum computing concepts. Okay, so we'll stop it for today here, and we will build from whatever we did today from here, from later on in the next session. Okay, so there is a 9 minutes I have. Let me see if there is any questions. Okay, there are plenty of questions. Okay, let me go. Okay, there is a question at 2:59. Electron or a photon, when traveling, it behaves like a wave when it interacts. Okay, and when it interacts, its interaction phenomena is understood by particle. Okay, of course, you are absolutely right. Let me take a new note. Okay, all right. So you are right actually. So like I was telling earlier, if the electron is a matter, by the way, it behaves like a matter, behaves like a wave. And photon is also it is, by the way, it's a wave energy, also behaves like a particle. Okay, right? So when it behaves like a particle, there is a called a Compton experiment. Compton. Okay. So in the Compton experiment, electrons were fired towards some particles, and as if it's like two billiard balls hitting, the electron is hitting like that and changing its momentum in particular direction, and it's getting a recoiling. That kind of a elastic collusion kind of a behavior it is showing. That ensures that assures the particle nature. But electron, by the way, it is wave in nature. Okay, when it comes to electrons, the matter also behaves like a wave, just like we saw. If you put the electron inside a one-dimensional box, we saw in three-dimensional box, the solutions were some sinusoidal function. If the electron is put inside a one-dimensional box, let's say in this case, the solutions would be sine kx, right? So where k we found earlier, propagation constant along x. So if I just find this, the actual solution, try to draw it, what I see is electrons could create a standing wave pattern. So let me call this is like say a ground state energy or a wave nature corresponding to ground state energy. Okay, and also it behaves like another wave pattern, standing wave pattern. So this may be correspond to n equal to 1. Okay, so and so on, I can have various ways, n equal to 2, we saw earlier, right? Okay, so there is a wave nature associated with the electron, there is a particle nature associated with the photons. Like as one of you pointing out, when they collide, the particle nature would come into the picture. Absolutely right. Okay, if I am correct, quantum basic has been already covered by Nivedita ma'am. Okay. So quantum basics in the sense, probably the Schrodinger equation and postulates of quantum physics, all those things. So what we would be needing for statistical physics, that is the part which we are covering in these sessions. 2 to the power of 10. Yeah, exactly. Okay. So probably you're talking in terms of 10 atoms case. Okay. Another question. Why is the number of accessible states decrease in the case of isolated system? Okay. So for the isolated system, for example, in the case of 3 atoms itself, okay, right? So all the 3, if let's say they are purely not interacting, so they are purely not interacting with the external means. So the only possibility they will have is all of them is existing like this. Okay, all of them are existing like this. I'm just talking only in this. Let's say these are the 3 possible cases if they are not interacting. Let's say I've prepared the system, prepared initially. right? So only 3 possible cases are there. So why I prepared initially? So I confined overall energy to, let's say, minus mu h. Okay, so that is what my intention is. If prepared initially with this much internal energy, in this case, okay, there is no go, right? So sorry, I have to remove even h there. Okay, overall energy is minus mu. In this case, magnetic moment is minus mu. In this case, the only possibilities are 3. When I have external intervention, in that case, I get another 5 cases. So overall, I'll have 8 possible cases. Okay, right? Yeah. Yes, how to model the interaction. That's what we will see, how to model the interaction. Okay, right? And microstates, yes, something at a micro level are microstates, something at a larger level, macrostates, micro and macro. Just see the difference. Thermodynamics, energy consumption, and the performance all are related in quantum computing. Yes, you are absolutely right. Thermodynamics, energy consumption, and performance are all related in quantum physics. Yeah, that's right. So that is what we were trying to address through these sessions. So I will, as I said, I will stop here. Okay. So I'll upload my notes, whatever is I have discussed today, right? So please go through it. Okay. And yeah, the book I am actually using for the sessions is this book, Statistical Physics by Reef. Okay. So let me show you. I think it is available in the net. Okay. So yeah, this is the book I'll be using. So in tomorrow's class, what we'll do, whatever the understanding we build today, from there we will go for the statistical ensembles. Okay. So this is a book. Okay, let me go. Where is the title? Yeah, it is the Statistical Physics by Reef, R-I-E-F. Yeah, Fundamentals of Statistical and Thermal Physics by Reef. This is a book. I'll be absolutely following only this book. There are other books also like Patria. Okay, so Patria, that is also available on the net. Landa Lifshitz. Okay, so these are the press skill notes. Doesn't discuss much of a statistical physics, but here and there regarding the entropy and all, it is being connected. So I would suggest you to please rely on the Statistical Physics by Reef book and Patria book, Statistical Mechanics by Patria. If you don't understand statistical physics by Reef, you can go to Patria. And if you want to go to higher level of understanding, Landa Lifshitz is very good book. Okay, so mainly I will be using this Reef book. Okay, so in tomorrow's session, we'll get into something called like I was saying, the partition function in the very early stage. So that is the part very important. That's a very powerful tool that we will understand in tomorrow's session. Partition function. Okay, right? Yeah.
Thank you so much, sir. The session was wonderful, and also participants are praising your notes. So thank you for notes also. And meanwhile, for participants, we are about to start your quiz, and it will be open very soon, within 5 minutes, and you can give it till tomorrow night, right? So make sure you attend this quiz. This is your third quiz, quiz number 3. And like always, you will get 30 minutes, right? So once you start, you will get exactly 30 minutes for giving this particular quiz. Right? So good luck, and we'll continue tomorrow at 2 p.m. Thank you.